Hello. So this week we're gonna do Learning Target 20. And this is broken up into two sections. So we're gonna do section 12.5 and 12.6. And the main theme of this is looking at the polar coordinate system. So in 12.5, that's all about polar coordinates. And then in 12.6, we're going to do a lot of graphing polar equations. So this video, we're going to focus on 12.5 polar coordinates, and you'll have a second video to watch that will be about graphing polar. So for this week, what I want you to do is look at these two videos, and then there's also a Desmos activity that will help you solidify everything. It's really important you do the Desmos activity as well, because especially 12.6 is all about graphing. I'm going to give you some background information in the video, but most of it is from you looking at these graphs yourself and coming up with the patterns and categorizing in your mind. So that's the thing that's going to solidify it for you, along with reading through the textbook and doing some practice problems as well. So please remember the videos are not meant to be the only thing that helps you learn this stuff. It's meant to be in sync with everything else that you have as well. So you have a lot of resources to help you, and we want you to really be making use of those resources right now to help yourself learn all of this material. So polar coordinates is the new kind of system we're going to look at. The polar coordinate system is a way of organizing things on a graph that's different from the x and y system we've had. So the x and y system, that's called the Cartesian coordinate system. The polar coordinate system is consists of something more circular and angular in style. So it looks like a bunch of circles put around, and actually I'll show you what it looks like. Let's go on Desmos. Right, so if I go on Desmos, I can get a polar grid out. This is what it looks like. So you have a bunch of concentric circles, and each of the circles have different radii on them. The radii tell you how far out to go in the circle. So if I go radius 1, that's going to be that circle of radius 1. If I make it radius 5, it's going to be the circle of radius 5. Now I can also get specific points on here by specifying what angle to move along. So it's like if I said radius 5 angle pi over 3, then I would land at radius 5 pi over 3. I can't write on this when I'm in Desmos, so just look at where the pi over 3 is on the video, and then that circle where it intersects, that's the point 5 comma pi over 3, radius 5 angle pi over 3. So in general, all our points are going to be radius and angle of the circle from the center. The center is the origin in a Cartesian coordinate. This is called the pole. And so we have the radius from the pole and the angle we move at. The points are not unique, right? So for example, radius 5 angle pi over 3. That's somewhere over here. But I could also write that as radius 5 angle, go around the circle, right, add 2 pi to it. So instead, I'd get 7 pi over 3. And that would give me the same point. I could also go in a negative direction on the radius. So instead of 5 pi over 3, I could say negative 5, and then go, so pi over 3, 2 pi, 3 pi, 4 pi over 3, going this way, right? That's 4 pi over 3. But if I go in the negative direction, I'll be going backwards on myself. I'll end up at this point as well. So all of these are the same point. And that's the main difference here, is like these points, they work on the circle radius system. And because of that, we can go back and forth on the radius depending on which direction we're moving in. Since we're controlling distance and direction, all these points are not unique. Whereas in a Cartesian system, like the point 2 comma 3, that's the only thing that describes that point. There is no other way I can describe getting to that point. But in this case, I can have multiple ways to describe the same point. So on your note sheet, you have a example graph and some points to graph out. I want you to try doing those yourself. And you should be able to just figure it out on your own from those points. The main thing we're looking at here is conversions between coordinates. So we think about where points are. If I think about the x and y system and then this system, right? If I have a point here and that's on one of these circles, well, so this would be an xy point, and that would mean that I have this x and I have this y, and I have a certain radius. So the radius would be, using the Pythagorean theorem, I know radius squared is x squared plus y squared. And the angle that I go at, well, that's the inverse tangent of y over x. So that gives me some conversions. I also know that x is r cosine theta, and y would be r sine theta. So I have all these conversions, right? So these are the main conversions between r, x, and y, and this would give me the angle if I need it as well. So those are conversion factors that we'll need. So let's practice converting some points. So if I had the point 3, 3 pi over 2, this is in polar. So this is r and this is theta. So I know r is 3, theta is 3 pi over 2. It helps to graph it out to see where it is. So 3 pi over 2, that's down here, and then 3 in this direction, that's somewhere down here. Well, just looking at it, I know it's going down a distance of 3, so it has to be 0, -3, right? But I can use these conversion values as well. I know x is r cosine theta, so that's r is 3 cosine of 3 pi over 2, which is 0. Y is r sine theta, which is 3 sine 3 pi over 2, which is 3 times -1. I get -3. And that gives me my point. Similarly, if I have the point -3, 5 pi over 6, I can do the same thing. R is -3, theta is 5 pi over 6. So if I think about where this is, 5 pi over 6 is over here, but then I go in the negative direction, so I'm actually going this way. My point is somewhere in the 4th quadrant. Well, x is r cosine 5 pi over 6. Well, cosine of 5 pi over 6 is root 3 over 2. Negative root 3 over 2. And so then I get 3 root 3 over 2 as my x value. Y value is -3 sine 5 pi over 6. And so this is -3 times 1/2. So -3 halves. So notice how this negative changed these values as well to make them the correct signs for the quadrant. I need a positive x and a negative y for this point, and that's what I get. So I can write my point down in x and y format. So those are conversions of points. Conversions of points should be fairly simple. What we're going to focus on now is converting between equations. So for example, if I had the equation x squared plus y squared equals 16, and this is where the real point of having polar coordinates is going to come out. So x squared plus y squared equals 16, we know that makes a circle. It follows the general format, x minus h squared plus y minus k squared equals r squared. So I know this is a circle with radius 4. But here's what I'm going to do. Instead of writing it like this in Cartesian form, where it's still a bit of a complicated equation, it has some squares in it, it's going to have square roots if I try to solve it. Instead, I'm going to change this to polar coordinates. Now, polar coordinates are based on circles and angles, so it should work out pretty nicely in polar. So if I think about my conversions, I know r squared is x squared plus y squared. So I can replace this with r squared, and then take the square root and get r equals 4. Now, I can do this without a plus or minus because no matter which way the radius goes, I can just change the angle to get the full circle, right? So if r is positive, then as I move around my circle, I'm still getting positive directions in each of those angles. I'll finish my circle anyway. The reason we need a plus or minus in Cartesian is because the top half and bottom half will change based on the sign. But in this case, the direction already brings us to the bottom piece of the circle. We'll get that whole circle just with r equals 4, because it tells us start at the pole, at the origin, and go out a radius of 4 in every direction from there. So we'll get every bit of the circle because we're going out in all these directions. So let's try another one. Let's do y squared minus 8x minus 16 equals 0. So this is a conic section, right? This is a parabola equation. We have only one term that's squared. So we know it makes a parabola. And so let's look at if we can try to write this in polar coordinates. That might be simpler. Maybe, right? We don't, that's the goal of the polar coordinates, is to try to make things simpler to look at, especially when you have a lot of these curved equations. So let's look at what we can do with this problem. So we have y squared minus 8x minus 16 equals 0. So I know that y is r sine theta, and I know that x is r cosine theta. So I'm going to start off using that. So y would be r sine theta squared minus 8r cosine theta minus 16 equals 0. So then I get r squared sine squared theta minus 8r cosine theta minus 16 equals 0. Now my goal is to have r equals something. So if I look at the format of this, I have r squared, r, and no r. That looks like the quadratic expression, right? If I had x squared minus x minus something equals 0, I can get x equals by using the quadratic formula. So that's what I'm going to do here. This is the most complicated type of problem you probably will have with this, where you have to do a lot of algebraic work with this, but it's good practice to try that. So if we look at using the quadratic formula to solve for r, I look at the coefficients of each to get the a, b, and c in the quadratic formula. So a here is sine squared theta, b is minus 8 cosine theta, and c is minus 16. So let's go with the formula. So negative b, so 8 cosine theta, plus or minus square root b squared minus 4ac all over 2a. So you get 8 cosine theta plus or minus square root 64 cosine squared theta plus 64 sine squared theta over 2 sine squared theta. And that gives us 8 cosine theta plus or minus, I can factor out this 64. So cosine squared plus sine squared is just 1 over 2 sine squared theta, which is 8 cosine theta plus or minus 8 over 2 sine squared theta. Divide out the 2. And I can factor out 4. And change sine squared to cosine squared, so I get everything in terms of cosine. And well, we said we don't need to use the... So let's split this up now. We have the 1 plus cosine. We'll factor at the bottom. And that gives me 4 over 1 minus cosine theta. Or I can use the subtraction version. So this problem does have a lot of steps, right? We're doing a lot of things to it, but it's stuff that you have done a lot of before. So here we need to factor out the negative to change this. it's just synthesizing a lot of different pieces of information to get this. But let's just review this again because there was a lot of steps. So the first thing we did was substitute r sine theta and r cosine theta for y and x, and we get this expression. This is already like an implicit version of the parabola. But then we want r equals something. And in the end, we get this as our r equals. But to get that on this particular equation, we had to treat it like a quadratic equation and use the quadratic formula. So we used the quadratic formula. And that's where most of the algebra came in. Right? So we used the quadratic formula. We got this expression inside the square root. But inside the square root, we could factor out 64. And use the Pythagorean identity, so just get 64. That became a square root. We took the square root of that. We just got 8. And then we just did some division. We used another Pythagorean identity and some difference of squares to ultimately solve this. So again, a lot of steps, but hopefully each individual step was something that you could follow along with. And it's stuff that you know how to do. We'll do one more problem on here, and then there are a lot more problems for you to try out on the sheet as well. So you can try those out, and then if you have questions, we can go over them. We'll go over some more of those in the live session as well, or during any individual office hours you might want to schedule with me. Let's do r equals... let's go the opposite way. So let's do r equals 4 sine theta. So here we have a polar equation. We want to change it into rectangular. So we know that r squared is x squared plus y squared. And we know that x is r cosine theta. We know that y is r sine theta. Right now, we don't have any of that substituted in here. What I have is a sine theta and an r. But I need r squared and I need r sine theta. So what I'm going to do is multiply by r on both sides. So then I get r times r equals 4r sine theta. So it's really important, especially when you're looking back at your notes on this. This is r times r. We did not square the r on both sides. We just multiplied a second r into it. So we get r squared equals 4r sine theta. Well, r squared is x squared plus y squared. And then r sine theta is y, so that becomes 4y. And then we can write this as a conic form, implicit, and get x squared plus y squared minus 4y equals 0. Let's do one more. So we'll do theta equals 11 pi over 6. So theta equals 11 pi over 6. If we think about this, we know that 11 pi over 6 is down here, and it's saying theta is that r could be anything, which means that it's this line. So anytime you just see theta equals something, that makes a line equation in polar form. So converting this, we know it's going to have to be like a y equals mx plus b kind of equation. So let's look at what we have. We have r squared is x plus y squared. That's not going to help us, but we have the r cosine theta, r sine theta. We could try using that. What we want to do is figure out the slope of this line to get the x and y. That's where the tangent is going to be useful. Because we all the way up here we had a tangent expression as well. Tangent inverse is y over x. So if we know tangent of this is going to be y over x. So tangent of 11 pi over 6, that's, so if I think about 11 pi over 6, that's negative 1/2 for the cosine of it. It's root 3 over 2 for the cosine of it, and negative 1/2 for the sine of it. And so we get negative root 3. So I know that's my slope of this line. And it's going through the origin, so I get y equals minus root 3x as the equation for this line. So that was converting between equations in polar and Cartesian coordinates. That's the main goal of this lesson. You should be able to comfortably convert from polar to Cartesian like these problems, or Cartesian to polar like these problems. Again, sometimes it can be really quick, sometimes it can be really long. And you should be able to convert points as well. So that's this first video, that's the first part, and then the second part is going to be graphing these and looking at what these graphs look like. And again, why we would use polar instead of Cartesian for some graphs.